to predictability. The milkman, the paper boy, evening TV. Everywhere you look, there's a heart, a hand to hold on to. Everywhere you look, there's a face of somebody who needs you. Everywhere you look, when you're lost out there and you're all alone, life is waiting to carry you home. Everywhere you look.
Hi, today we'll be talking about Chapter 2, Three-Dimensional Geometry, Intermolecular Interactions, and Physical Properties. First, we will begin with factors that determine molecular geometry, then later discuss the intermolecular interactions. First, we'll begin with VSEPR, which stands for valence shell electron pair repulsion. The valence electrons around an atom are treated as an electron group. This can help quicken the process of determining molecular geometry.
I'm talking to you about the basic principles of VSEPR. Electrons in the Lewis structure are viewed as groups. One lone pair, one single bond, one double bond, one triple bond.
Oh, baby, a triple!
Each constitute one group of electrons.
Number 2, the negatively charged electron groups strongly repel one another, so they tend to arrange themselves as far away from each other as possible. With 2 electron groups, it'll be 180 degrees apart and it'll be linear. With 3 groups, it'll be 120 degrees apart and it'll be trigonal planar. And with 4 groups, it'll be 109.5 degrees apart and it'll be
The
tetrahedral.
VSEPR theory is electron geometry, and it describes the orientation of electron groups about a particular atom. Over here in the chart, you can see the corresponding bond angle and shape for each one. For linear, looks like this with 180 degrees, trigonal planar, 120 degrees, and tetrahedral, 109.5 degrees.
In rule number 4, we're going to talk about molecular geometry. And the molecular geometry describes the arrangement of atoms about a particular atom. And because the atoms must be attached by bonding pairs of electrons, an atom's molecular geometry is governed by its electron geometry. And over here in this table, we can see the number of bonded atoms in groups here. For 2, it can be linear, bent, with 2 bonded atoms and a lone pair, and that's 120 degrees. Or it can be bent with 2 lone pairs and 2 atoms, and that'll be 109 degrees, 0.5 degrees. In 3, it can be trigonal planar with 3 bonded groups, again 120 degrees. Or it can be 3 bonded atoms and 1 lone pair, which will be 109.5 degrees. And then in 4, it can just be 4 bonded atoms, which will be 109.5 degrees.
I'll be talking about the dash wedge notation. First of all, a straight line represents a bond that is in the plane of the paper. A wedge represents a bond that points towards you. A dash represents a bond that is pointed away from you.
A difference in atoms will have a difference in electronegativity. The more electronegative the atom, the more negative charge that is on that atom, and vice versa. This is a polar covalent
The
bond.
dipole moment of a molecule is a measure of the magnitude of its dipole. The direction of a dipole moment is toward the negative charge, and the magnitude is reported in units of.
A dipole moment is a vector, and a vector, by definition, has both magnitude and direction. If a vector cancel each other out, then you have a nonpolar compound. And if they don't, then it's polar. Here we have some examples. In this FH bond, fluorine is the most electronegative, so it pulls the electrons that way, which has a net dipole of 2.2 divide. And in this one, we have an example of them canceling each other out. And the carbon bonded to 2 oxygens, which they both have a vector going opposite ways, so it cancels each other out, so it has a net dipole of 0. And in this one, we have water, which oxygen is the most electronegative, so it pulls the electrons toward it and has a net dipole of 1.8 divide.
Now we're talking about intermolecular interactions or forces, and these are interactions between molecules caused by structural differences of functional groups. And these functional groups can also affect the physical properties of molecules. The first type of intermolecular interaction is ion-ion. It's the strongest one because it is between 2 ions which have very high concentrations of positive and negative charges. And A plus and Cl minus is an example of this.
Dipole interactions arise because the positive end of one molecule's net dipole is attracted to the negative end of another's. Here we can see a dipole-dipole interaction. We have oxygen, which is highly electronegative, and carbon, which is not so electronegative. The electrons from the carbon will be attracted to the oxygen, creating the dipole-dipole.
Now we're going to be talking about hydrogen bonding. Hydrogen bonding is bonding between a hydrogen and a hydrogen acceptor, which can be nitrogen, oxygen, or fluorine. And the strength of this bond depends on the concentration of charge. So in this example, we have a hydrogen bond donor, which is represented by D and can be nitrogen, oxygen, or fluorine. And it's covalently bonded to a hydrogen. And that hydrogen is bonded through a hydrogen bond to a hydrogen bond acceptor, which is nitrogen, oxygen, or fluorine. And this is due to its highly electronegative nature and its ability to have a lone pair. So it forms a partial negative and a partial positive on the hydrogen.
An example of intermolecular forces is London dispersion forces, which are dominant intermolecular interactions between nonpolar molecules. Our two nonpolar molecules here are the two carbon elements right here. The bond that they form will be an induced dipole, and because they're the same element, it will be polar, and they could really care less about being next to each other, which is kind of like me and Board Guy. We might have a bond, but we don't really care about each other. These are the bonds in order from strongest to weakest. Our strongest is ion-ion, the second is hydrogen bonding, third is dipole-dipole, and last is London dispersion forces.
We're going to talk about solubility. An easier way to remember is polar dissolves in polar and nonpolar dissolves in nonpolar. For the polar, for example, NaCl is an ionic compound which dissolves in water, and what it does, it disassociates into Na plus and Cl minus. And for nonpolar, an example would be methane dissolving in hexane. However, methane can't dissolve in water because methane is nonpolar and H2O is polar. Now, polar protic tend to solvate cations and anions very strongly, and polar aprotic tend to solvate cations very strongly, but not anions. Briefly, soaps. Soaps work because one end of the molecular species is very hydrophilic and the other end is very hydrophobic. Also note that detergents are more effective in hard water than soaps are.
Talk about boiling points, we can refer back to this chart. Boiling point is caused by intermolecular forces. From strongest to weakest, ion-ion is the strongest one, and London dispersion forces is the weakest one.
Chapter 2. With the Vesper theory, when you have two groups, they'll be separated by 180 degrees. When you have three groups, it'll be separated by 120 degrees. When you have four groups, it'll be separated by 109.5 degrees. With angle strain, it's geometric constraints that force an atom to deviate from its ideal bond angle. With dash wedge notation, if it's a dash, it's going to a plane away from you, and if it's a wedge, the plane is coming towards you. With vectors, they have direction and magnitude, and they can cancel each other out. With dipole moment, it's a measure of the magnitude of the dipole. And solubility is like dissolves like, with polar and nonpolar in mind. With intermolecular forces, with the ranking from strongest to weakest, you have ion-ion as the strongest, which is two oppositely attracted elements. The second would be hydrogen bonding, which involves hydrogen, a hydrogen acceptor, and a hydrogen donor. With dipole-dipole, you have electronegative atoms bonding together, but not necessarily with their own charge, so they'll have partial charges. Dispersion forces, that is nonpolar bonding between two like-minded elements as far as electronegativity goes.
Vesper. Why are you laughing?
I'm not laughing.
That determine molecular geometry. Stands for valence shell quicken the process of determining the molecular geometry. God, what?
Oh boy, here we go.
Okay. Oh my god.
Gosh,
Oh my
not
god.
again.
I'm so sorry. Listed. Can we just
The recommended amount of dedicated RAM I should have to this.
That's how I go.
One single bond.
The recommended amount of dedicated RAM.
Okay, today I'll be talking to you about the basic principles of Vesper.
109 degrees between each, and we'll do it again because I messed up.
Yeah, I have to.
Yeah.
Should you say
That's
it? It describes the rotation. Yeah.
The recommended amount of
You guys are like,
Dipole moment of a molecule is a moment.
Whoop! Surprise! Cancel each other out. Then you have a non-polar compound. I did it again.
To the negative end of another's. Here we can see it. Version is an induced dipole. You might be wondering, where is it? It's right here.
That's all, folks.